Welcome everybody. It's a pleasure to have Dr. Marika Asgari here today. Thanks a lot for accepting our invitation. Dr. Asgari is a lecturer at the University of Newcastle, working on understanding the large-scale structure of the universe. She obtained her PhD in 2015 from the Institute for Astronomy at the University of Edinburgh under the supervision of Professor Andy Taylor and Professor Catherine Hamans, working on weak lensing and understanding the nature of dark energy. Marika continued this work as a postdoc at the same institute, followed by a position at the University of Hull. She's a coordinator for the Kilodegree Survey, KiDS, as well as being a member of the Euclid Mission and the Rubin Observatory's Legacy Survey of Space and Time. Today, she will talk to us about cosmology with the final KiDS data release. Marika, please start in your own time.
Hey, thanks a lot, Jackson. So since Hull, I've moved to Newcastle now. And yes, it's been like a couple of years that I've moved there. So today, yes, I'm going to talk to you about large-scale structures. I'm going to just talk about KiDS today, although I know in the title it says KiDS to DESC, but it's just to point out that KiDS, or the Kilodegree Survey, is an imaging survey that has taken all of its data now. So we're still doing some analysis with it, but I'm moving to mostly focus on Rubin LSSD or DESC analysis. Okay, so this image you can see here is an image of the sky, and the dark bits are showing the galactic plane, and then the colored parts are showing mass maps from KiDS, so the last data release. So you can see that KiDS data is taken in two narrow bands, and one of them is on the equator, the other one is in the south. And these mass maps are showing basically what we expect the large-scale structure to look like if we project them. So the main probe that I'm going to talk about today is cosmic shear. I will maybe at the end touch on some of the other large-scale structure probes, but we had analysis from cosmic shear that came out recently, so this is what I'm going to talk about today. So let's look at how cosmic shear works using this image here. So if you have okay, so if you have galaxies in the background, like the blue ones you see here, and the light passes by massive structures, that's the pink things you see on the way, then we observe it. Because of the gravity of these structures, we expect the shape of the galaxies to be distorted as the path of light distorts. Now, if you have two such galaxies in the background and their light passes by similar structures, they will be similarly distorted. So the shapes of the galaxies that we observe are going to have some kind of correlation. And this correlation is what we actually measure as the cosmic shear signal. So the 2-point statistic, that is the standard way to do cosmic shear, basically is always based on this type of 2-point statistic. Now that was just a cartoon way of saying how cosmic shear works, but in practice it's much more complicated, because in practice you can't really measure any signal if you just have a couple of galaxies, because the cosmic shear signal, which comes from the lensing by the large-scale structures, is a very weak signal. It's not just weak lensing, it's very weak lensing. So how do we do this? We have to have high resolution and deep images, so we can get images of millions and millions of galaxies, so tens of millions, hundreds of millions of galaxies. But we also have to have multiband imaging, and this works in two ways. One is that it helps us distinguish between galaxies and stars, so we can make a catalog, and then in a second way that it helps is to help us estimate the redshifts of galaxies, and that's something we need to be able to model the signal that we saw in the previous slide. Okay, so you have your catalogs, you found out which ones are galaxies, which ones are stars. Now we need to measure the shapes of the galaxies. And to measure the shapes of the galaxies, we also need the stars. Because say if you have a telescope on the ground, you have the atmospheric effects that creates like kind of blurriness in your images, which is called point spread function. That is because if you have a point, like a star, in your image, this effect, or the seeing effect sometimes called, it turns it into, it spreads it, and there is a functional form to it. So it's point spread function. So in order to model the point spread function, we use the stars because we know that they're supposed to be point sources. So we can use them to model it for the galaxies where we don't know what is the original shape. It's the same if you have a telescope in space. You don't have atmospheric effects, but the telescope itself will create this kind of seeing effects. And sometimes that can be more complicated. Now, as I said, you need the multiband imaging to estimate the redshifts of the galaxies. And that can be done by, say, for example, you have spectral energy density templates for your galaxies, and then you shift them to different redshifts and apply these photometric bands on them, and then compare it to your observations, and then find a best fitting model. So then your best fitting redshift based on the spectra will give you galaxy redshifts, and this is called photometric redshift. Now, both photometric redshifts and the shapes that we measure from the data can be biased, and they have different reasons why they can be biased. For example, for galaxy shapes, you have noise in your data. You might have galaxies that are blended on top of each other, and generally your shape measurement method might not be perfect. For redshifts, because you only have information in a few bands, you're not going to be able to estimate things accurately. And then on the other side, if you're using the spectral energy density from galaxies that are like closer to us, so you have more information about them, it doesn't mean you have all the information about all galaxies that exist in the universe. So you can have sources of error in both cases. And also in this case, you also have error in your measurements. So you have noise there too. So in order to handle these biases that can be in these two main ingredients that we need from the data, we need to calibrate them. And this calibration is normally done using something where we know what the truth is. That could be some data that is higher qualities, like spectroscopic data, if you have redshifts, or it could be using simulations where we know what the input is. And often it is actually a combination of both of them. Okay, now what you do is you divide your galaxies based on redshift into tomographic bins. And this allows us to see the evolution of structures, so we can get a better signal, more information from the data. Then what we do is we take the correlation between shapes of all the galaxies, pairs of galaxies with different distances. So we will have correlations within the tomographic bins and correlations between tomographic bins. So cross correlations and autocorrelations. Now that we have the signal, we need to have some kind of model to compare it with. So you choose your cosmological model. Today I'm going to only talk about flat-LCDM, but we have some works down the pipeline. It's going to come out very soon, within the next month probably, where we look at other cosmological models as well. But let's say you use flat-LCDM, but the pipeline is going to look the same, whichever method you use, whichever model you use. And then you need to turn these cosmological parameters and cosmological model to large-scale structures. And that's normally done using either some kind of analytical model, for example, the HALO model, or simulations, or possibly a combination of both of them. Now, if these simulations and these analytical models, they're normally just based on dark matter, so it might not have all the effects, and we'll get to that you have to correct for these two. Then you need to turn your large-scale structure information into something that looks like the signal that you want to compare with. So if it is correlations between shapes of galaxies, that's what you have to model. And you have to model the covariance for your signal. So in order to do that, we need an input from the data, and that's why there is an arrow from galaxy redshifts, because where the galaxies are will really dictate what signal you have. The further away they are, there will be more matter, intervening matter, which means that you should get more higher signal. But before we can compare the model signal and the real signal, we need to make sure that we take care of nuisance effects. Now, these nuisance effects are basically astrophysics. So cosmologists like to call astrophysics nuisance, because we like to think about galaxies as just like little stickers on the sky that follow matter. But we know that that's not the case. They have their own rich lives and they do things that are beyond cosmology. So the things that are important for recleansing are two main effects. One is baryon feedback. So this is feedback you get from active galactic nuclei, for example, or supernova explosions, where a gas and matter is pushed out of the centers of halos. So that changes the profile of halos and that moves things around, which means that your power spectra are going to be different. So you have to model this, but this is a relatively smaller scale effect, but not that small scale. So it's still important to some level for cosmic shear. And then the other effect is intrinsic alignments of galaxies. So the thing we want to measure is correlation between shapes of galaxies, but galaxies might already be correlated because of where they were born and how they were formed. So that will be a signal that can be confused with the cosmic shear signal. So we need to be able to model that as well. So once you have all of this, you can really model your signal and also add any other effects that you have. For example, maybe your calibration introduces some kind of error, and then you can include that error in your modeled signal or your modeled covariance matrix. And then compare your real signal and model signal in a likelihood analysis. And then you do your inference, which is basically making your contours and reporting your parameter estimates and this sort of thing. But the thing that we should never forget is blinding. And this is something we've been doing consistently within KiDS from the first data release for KiDS 450, first analysis of KiDS for cosmic shear for KiDS 450. And that is because we are in a situation where we have these tensions. That's why we have the action in cosmology, and depending on which side you're on, you might want attention or you don't want attention. And then because there are so many steps in this analysis, and actually each of these boxes have their own like mini steps in them. So like each of these boxes are kind of like their own field almost. So you can make choices to get what you want if you know what the final result is. So blinding, basically what it does is that it kind of immunes you from this kind of choice making, because you get to the end of your analysis and you don't know the true answer. So you won't be able to tell if you have tension or not, which means that all your analysis choices are done because of some other reason, not because you want tension or you don't want tension. And this is what we've done for all the analysis. Okay, so a little bit about KiDS. There's an image of the telescope here. It's a telescope that's in Chile on Paranal, and it's an ESO, European Sun Observatory project. So KiDS is a weak lensing specific survey, which means that it has very good seeing. So the best conditions were kind of like used for taking the images for KiDS. So we have an R-band mean seeing of 0.7 arc seconds, so we can get good shapes. And then KiDS has a sister survey called Viking, and together they have 9 photometric bands. And this is very important because more bands means we can get better redshifts, and 9, by the way, is a large number for a cosmic shear survey. Most of them have between 3 to 5. So that's one thing that makes KiDS quite special. We've collected all the data, and it's about 1,350 square degrees. If you're familiar with the KiDS 1000 analysis, I do some comparisons between the two as I go along. So one comparison is that we had a 35% increase in area, but we managed to almost double the number of galaxies that we can use. And I will go through why that is the case. So it's not just a 35% increase in data, it's much more than that. Why is it not showing? Aha, yes. So this talk is mainly going to be about these papers here. And these were papers that came out this year. And we look at cosmic shear, constraints, consistency within the data, and also with some external data and joint constraints, how the redshift calibration is done, the data release paper, which describes all the details of the data, and a covariance paper. I put the pictures of these 3 gentlemen here because they were they are early career researchers who led these papers, basically. We also have a talk on Cosmology Talks where we go into some more details that I won't cover here. Okay, so I want to show this picture before I go into why we managed to increase the number of galaxies. So this is basically a zoom in on the bands that you saw in the first slide, and you can see what the resolution is and how it looks like, and you can see the moon shown on top of it, so you can kind of get like a kind of handle on the scale of the image. All right, so how did we increase the number of galaxies? So one of the main things that changed between KiDS 1000 and KiDS-Legacy was redshifts, and there are different aspects to that. One aspect is that we managed to get new simulations, which meant that we could push our redshift base to higher redshifts. So previously we had 5 redshift bins and we went to redshift of 1.2, but now we have 6 redshift bins and we go to redshift of 2. And then remember that these higher redshift galaxies, they have more signal because there's more intervening matter. So they can increase the information by quite a bit. So you can see here the redshift distribution for the 6 bins, and the gray region here is showing how the bins were defined. So the bins are defined using our spectral energy density fitting method, which is using this code called BPZ. And then the green distributions are what we get after calibrating that. And I'll go through how the calibration is done in the next slide. So one of the reasons we managed to increase galaxies was because of the 6 bin, but this wasn't the only reason. So I'll go through the other reasons in the next slide as well. All right, so how do we do the calibration? So first of all, as I said, we use this code called BPZ to get the first estimate. And then that estimate is just used to define the redshift bins. That's all it's used for. Then we have the first step of calibration. And that is when you calibrate against spectra for a subset of the galaxies that you have in your source sample. So your source sample is all the galaxies that you want to do cosmic shear with, and the calibration sample is a subset where you have spectra. Now, the way we do this calibration is using a method called SUM, or self-organizing maps. And this is machine learning method, and basically all it does is that we give it the colors, so the 9 colors here, and then we say, okay, can you divide my source galaxies into a number of groups where the colors are similar to each other. And then what it does, it gives you back this map. So it's basically kind of like flattens the 9-dimensional color map that you have into 2 dimensions. And each of these cells here are showing, say, for example, it might be showing the redshift of the mean redshift of galaxies in each of the cells, or it might be showing the number density of galaxies in each of the cells. But all the galaxies that are in one cell have similar colors. So once you've done that, then you can ask, what happens if I put my calibration sample into the same cells? So you do that, put them in the same cells, and then you can match the galaxies that are in your source sample and in your calibration sample using this map. So using the self-organizing map. So then once you made that connection, you assign the redshifts to your source sample, and then you get a better estimate of the redshifts. So this is the first step of the calibration, but then there's a second step to the calibration, and that is simulation based. So in the simulations, basically, we are asking the question, what happens if we apply the same method, so the sum method, but to our simulated data with 2 samples that resemble our source sample and our calibration sample. So we do the exact same exercise with the simulations, but there, because we know all the redshifts, all the true redshifts, we can then estimate any remaining biases and errors, and then add that in our analysis. Okay, so back to why we can add more galaxies. So if we look at the KIDS 1000 sample for calibration, so these are the spectra. This is these orange points are showing the galaxies that we had for that. And here we have like different surveys, spectroscopic surveys, spectroscopic samples, and they are pointing at different parts of the sky. So you can see redshift along the longer axis, and then angle around the smaller axis for all of them. So the orange ones are the previous data. Now the green ones are the new data. And you can see that we have a lot more spectra. So it is like about 3 times as much. So because we have more spectra, it means that we can calibrate better, first of all, and we can calibrate more galaxies. So if I go back to a slide here, imagine you made this map for your source sample, but then when you tried to put the calibration sample in it, some of the cells didn't have any galaxies in them. What do? So you don't have any estimate of the redshift of those galaxies. So what we did was just to remove these from the sample, which means that if you have fewer calibration samples, you will have to make your sample generally smaller. So that was another reason that we could add extra galaxies to our samples. So we had better calibration sample, which meant we could keep more of our galaxies. All right, so this is the redshifts. Now let's see what is the final result once you do the analysis. So we normally expect to get something like this. It's called the cosmic banana. It tells us how the degeneracy between sigma 8 and omega m work. And we are looking at 2 different statistics. I will talk a little bit about our fiducial statistic in a few slides, which is called Kosebe's. But you can see that the 2 statistics basically give us the same results. So the blue and orange are almost on top of each other. And the main thing here is that the Planck contour is now has kind of full overlap with the KIDS one, so we don't have the tension anymore. So I can hear already people saying, boo, don't want that, but that's just how it is. And we were shocked when the unblinding happened as well. So we had to ask our unblinder multiple times if they were sure this was the correct blind, and then also check it ourselves. But it seems to be the case. Okay, because we have that degeneracy in a cosmic banana, we normally look at this other parameter called S8, and the definition is here next to the left-hand plot. And here we're comparing our results with the latest results from stage 3 surveys. So we have DESC-Y3 and HSC-Y3, and you can see that the three results are pretty consistent with each other, maybe HSC a little bit lower than the other ones. But also I need to point out that the DESC-Y3 data here, DESC-Y3 analysis here, is from the DESC plus KiDS paper. Because if you remember, the original DESC analysis was lower, had lower S8 than this, basically. So this is using the hybrid analysis from the DESC plus KiDS paper. And the other two plots, so the middle one, if you focus on the middle one, this is looking at another parameter which is similar to S8, but has a different power for omega m. And that power is fitted to the banana, so we find the narrowest part of the banana. And if you do that, you get a power that's 0.58 instead of the 0.5 that you have for S8. And normally we look at things in this space because it makes the cosmic shear constraints the most attractive, so it makes them tighter. And if you look here, you see that with Planck, we have about 0.7 sigma difference. And you can look at the differences with the other two as well. So we are 0.7, about 0.75 higher than DESC-Y3 and 1.8 higher than HSC. So they're all consistent with each other, basically. All right. Okay, so let's go back and kind of compare some stuff with KiDS 1000. So the main thing is that the error on capital sigma 8 has decreased by quite a bit. So in KiDS 1000, we had 0.02 roughly, and now we have 0.015. So this doubling of the number of galaxies has shrunk the error bars. And then we also looked at a lot of variations of the analysis, which made sense. For example, looking at different intrinsic alignment models, or looking at different ways to calibrate the data. And also at the bottom, you can see what happens if you remove each of the redshift bins and redo the analysis. And it seems like everything is consistent, nothing shifts the analysis by more than 0.5 sigma, with one exception, and that exception is the -2 delta z. So you can see that it shifts the error bar kind of higher, but that is something that we expected. And it probably should have not put it in this plot because it makes it a little bit confusing, because -2 was the simulation we used for KiDS 1000. And that was a simulation that didn't have high redshifts. And that's why in KiDS 1000, we couldn't have the 6-spin. Now for Planck-Legacy, we have scaled simulations which has higher redshift. And that's why we could include the 6-spin. So if you do your analysis with -2 without doing any redshift cuts to KiDS Legacy, you do expect to get a bias, basically, because you just don't have these galaxies at higher redshift. So, we do expect that to happen, and that's fine. So other than that, everything seems to be consistent. Okay, well, so far what I've been talking about made it sound like everything is fine, and it was all like easy sailing, but it wasn't because of B modes. So what happened was that we we're very close to unblinding 1 year before the submission of the papers. And then we discovered that there are large B modes in our data. But what are B modes? So if you have, so imagine you have a large kind of spherical mass in the middle of each of these images. If you have a large spherical mass there, you'd expect to get alignments that are tangential around it. So that's the E mode, but the left-hand side one. Now, if you had a large void in the middle, you would expect to get the E mode, but the radial alignment one, so the right-hand side one. Now, the two kind of like curly shapes that you see in the B modes are not something that we expect to get from lensing. So if you do see this kind of alignments in your data, it's a sign that something has gone wrong. Now, there are some models and some like intrinsic models that can create very, very, very small B modes, but they are normally much lower than the noise in our data, at least current data. Which means that with current data, if you see large B modes, it means that you have some kind of systematic. So I said that I will talk about our statistic a little bit. So the fiducial statistic that we use is called CosMVerse. That's complete orthogonal sets of EB integrals. So this set of statistics, they were designed to be able to separate these two modes completely. And it's important to be able to separate them because it's a systematic test, obviously, and we do want to, if you wanted to test like your intrinsic alignment model or your strange cosmology model that creates B modes, you can only do it if you can separate these two. And then this special thing about this statistic compared to, say, I don't know, pseudo-CLs or something like that, is that it can cleanly and completely separate E and B modes when you have limited data. And that's always the case because we cannot measure the correlations at 0 degrees because the galaxies will be on top of each other, so you can't measure their shapes, and we can't do it for infinite distance either. So when you have these limits, and also you have like other systematics, you know that they start to get large when you go on large scales or get on small scales, so you want to make these cuts. And the CosMVerse is what you need to use to be able to separate these two modes. So, and then it has other benefits as well, like it does data compression naturally, it's less sensitive to barren feedback and so on. So that's why it was our fiducial method. And these two equations here show how you go from E mode power spectra, so these are power spectra for lensing, to the CosMVerse E modes, and B mode power spectra to CosMVerse B modes. And it's just an integral with some weight function, basically. So it's a linear transformation. But for the data part, we don't use power spectra. We use the correlation functions that I've been talking about a lot. And we know that correlation functions mix E and B modes. And there are two of them, psi plus and psi minus. And this is because the quantity we're measuring, shear, it has two components. So to get all the information out of it, you need to at least create two correlation functions. So once you have the two correlation functions, you need these TNs, which are filter functions, and then again, it's an integral over them and gives you the EN and BN. So we measured this BN, and it turned out to be very significant. So when we first did the measurement, I'll make this a bit smaller. Yeah, when we first made the measurement, we were at a p-value that was super small. So you can see that p-value was like, I don't know, 10 to minus 9 or something like that. So that cross that you can see there. So it couldn't have been just a fluke or anything. It was really a significant detection of B mode, let's say. But then we asked the question, why is this happening? So we had to go through all the steps of the analysis that I've shown backward, and then we found that it was the very, very first step that had an issue. And then the way we fixed it was by removing some of the data where we found out that there was some issue, and then that meant that we could decrease the B modes. So the significance of the B modes. So you see these crosses here, and then the circles are showing the different p-values depending on how much of the data we're cutting out. So the more data we cut out, the p-value will get better. But it's getting better much faster than how much information we're losing. So it's not because we've just made error bars bigger that we're getting a smaller p-value, a larger p-value. And then at the end, we went with the threshold that gives us the green circle. So this one. Okay, and then we asked the question, how much does this affect cosmology? Because we wanted to make sure that even though we've removed the B modes, we're not affecting cosmology. And it seems like all the different points, even the ones that have very bad p-values, still give you pretty much the same capital sigma 8. So this is showing sigma 8 minus the fiducial sigma 8. And the fiducial sigma 8 is the green one there. And the error bars are just the error from doing the fit. All right, so once we fixed that, which took 1 year to find out and fix, we had our new results. And the new results, as you know, don't have tension with Planck, but our previous data release, we had significant tension. So we had 3 to 4 sigma tension. And everyone asks what happened. So this is where we were. And then a couple of years later, we did some reanalysis of it and used the updated scale cuts, which was used in the DESC plus KiDS paper, which shifts things a little bit higher. So it makes the tension a bit smaller. And then we asked, okay, so these last few that I'm going to show you are all analysis that's done for Planck-Legacy. So we have a new redshift estimation method. And we asked, okay, so if we use a new redshift estimation method, but with the same data, what happens? And we see that it shifts it by about 1 sigma. So this is like the largest single shift probably that we see. And then we ask, okay, we have the new redshift estimation. What happens if we also use the full calibration set that we had for Planck-Legacy? And that shifts things by a little bit. Then we do the same, we do a few versions of the analysis, but now using the legacy data. So one thing I should mention is the KiDS data and legacy data, although the main difference is that one is 35% more area, the whole data was reanalyzed because we got a new astrometry data from Gaia and so on, and so all the tiles were reanalyzed. So now we're asking, okay, if we analyze the KiDS legacy data that is shared with KiDS 1000, so the same tiles as KiDS 1000, but newly calibrated or reduced, what happens? So this also shifts things a little bit. Then if we add the 6th bin, so the higher redshift galaxies, that doesn't shift the center, but it just makes the error bar smaller. And here we have a different intrinsic alignment model, which also doesn't seem to have a big effect. And then finally, if we add the additional data, that 35% that wasn't in KiDS 1000, then we get another like about 1 sigma shift. So, and these were all done, these extra analysis were done after unblinding, where we didn't change the final result. because of them. We just wanted to understand why things changed, basically. And it seems like every single thing is moving us in one direction, unfortunately. Okay, so I'll talk a little bit about constraints on astrophysics. So we have intrinsic alignments, and we can that happens because of where the galaxies are formed. And normally we can think of it in terms of the type of galaxy. So red and blue galaxies, or disk and spherical galaxies, tend to have different response to intrinsic alignments. And what we did was to try a few different intrinsic alignment models, and our fiducial model is different now from what we had before. And this is a halo mass dependent model where we assume that only red galaxies align intrinsically and blue galaxies do not align, which seems to match with observations currently. And then we have two free parameters which are heavily prior dependent. And then the plot here is showing the fit to our intrinsic alignment values for the different models we have. So NLA is like the basic model that everyone uses. And then we have two other models. One has a redshift dependence, one has a scale dependence. And you can see that the results are all relatively consistent. The other astrophysical effect is baryon feedback. So what we used in our fiducial analysis is HM code 2020, which is halo model based approach, and it was calibrated against Bahamas. It basically says, okay, if how much does my AGN blow up my profile based on the gas fraction. And I just want to also advertise the Halo model review that we wrote a couple of years ago, if you want to know a bit more about that. And then we compared our posteriors for our AGN feedback to the new set of simulations, which are similar to Bahamas, but is newly done, to see how it compares, and it seems to be within the range for this flamingo simulations. Okay, so another part of the analysis was internal consistency of the data. Because we don't have very much time, I'm going to kind of like summarize it a little bit. We did three tiers of tests. The first tier was looking at just one number, basically. So it's evidence-based metrics like base factor and suspiciousness. But for all the tiers, we're kind of doing the same thing. We're saying, okay, if I divide my data into two sections, it could be like, say, the two bands of kits, north and south, or it could be one redshift bin versus the other redshift bins, and then analyze them separately, and then analyze them together, which is the fiducial analysis. Which one of them is preferred by the data, the separate analysis or the one that's done together? So in tier one, we just give one number to say which one is preferred. So do you prefer separate sets of cosmological parameters or a joint set? In tier two, we actually look at the parameter differences. So here, for example, this is showing the parameter difference between the two parts of the data. And then we're asking how far away from zero that is. And then in tier three, we actually look at the data space. So here, imagine you have part of the data, one part of the data, and you've done the fit to that part. So that would be kind of the gray one. And then you say, what does the other parts of the data predict for this part? And that's shown in green. And then you ask yourself, are these two consistent with each other or not? So when we do these three tiers of analysis for Planck-Legacy, we don't really find anything out of the ordinary. Everything seems to be consistent. I'll show you some examples of it here. So we had quite a lot of different divisions that we've done. One is redshift bin level. So for example, here, all combinations with redshift bin 4 versus all the rest of the data. And the n sigma here you see is the significance of these differences. So for redshift bin level 1s, all the n sigmas were smaller than 1.39. Then we had auto versus cross correlation, so auto correlation between redshift bins, and that they are very consistent. Then we have scale dependent, so like large scales versus small scales. Again, they are very consistent. Then we have catalog level divisions, so kids north versus kids south. Again, very consistent. And then we also did a red versus blue analysis because we expect them to react to intrinsic alignments differently. Also very consistent. And here is showing the tier 2 results for some of these combinations. And you can see visually that the contours all match up with each other. The fiducial result is shown in dashed, but then the two divisions are shown with the different colors. In the internal consistency paper, we also looked at combinations with some external data. So we have combinations with BAO data and Pantheon. So you can see that what when you do these combinations, basically you'd break the degeneracy with omega m, but the S8 value is mainly driven by kits. So that doesn't really change. And then we also combined with this Y3 data. So this pink one is cosmic shear only. And if you add the other ones on top of it, you get the black one, and you can see that it's very competitive constraints compared to Planck. And I want to also advertise the covariance and modeling paper a little bit. It describes all the different ways that this code works, and it's a public code. You can use it. It's an example covariance that it produces. And any kind of 2-point statistics you have, it can give you a correlation for a covariance for it, basically. And then finally, the thing that I'm working on right now is to do a 3x2 PT analysis for kits only. So that is cosmic shear, galaxy clustering, and galaxy-galaxy lensing. So this paper that came out, I think it was maybe accepted 2023. It's doing almost the same thing, but with the previous data, and it doesn't have cosmic shear in there. So it's a 2x2. But the difference between this 3x2 or 2x2 analysis with, say, the kits plus BOSS 3x2, so Heyman's et al., or the DESC Y3 3x2 is that we are really pushing to smaller scales. And the reason we can do that is because of Halo model and because of an addition, the addition of a 1-point statistic, which tells us the abundance of galaxies based on their stellar mass or stellar mass function. So we can extract small scale information, which means that if we look at our contours, so the blue one would be from this analysis here, and then if I say plotted the BOSS results here, you see that the areas of the two contours are pretty much exactly the same, although BOSS has 9 times larger area. And this is all thanks to being able to go to smaller scales. So we're trying to do this with Planck-Legacy now. Okay, and I will end here with some things that I'm looking forward to. KiDS extended cosmology papers coming out very soon, probably next month. And then the 3x2 analysis that I explained. We are also working on a 6x2 analysis, which also combines spectroscopic data. That's why it doubles the 2-point statistics. And also we're working on beyond 2-point analysis with Planck-Legacy. And of course, there's the Rubin LSSD first cosmology results, which will come in a few years, but the data is being collected now. Okay, thank you very much.
Thank you so much. Very, very interesting. Does anyone have questions? So, Florian?
Hello, Marika. Thank you very much for this talk. So I wanted to ask about your simulations. So usually when you use this kind of simulations with inflationary potential, what kind of potential energy did you use for the inflations? Because I see in your article that you fit for the spectral index and for the log power of curvature perturbations.
Which simulations do you mean?
The this the simulations that you are using in this KiDS cosmological constraints from cosmic shear with the complete in the latest article. So it's
Oh, that
basically
the
what you are showing, no?
do you mean right at all?
What kind of potential energy are you using? Because your values for spectral index are very far from from the flat CDM.
So if you're talking about the right at all paper, we don't actually use simulations directly for the analysis because the simulations that I mentioned, the skill simulations, they're only
Yeah.
used for calibrating the shapes and the redshifts.
So you are
Um,
not using a model?
so the
So
model we're using is the HM code model, which gives us a nonlinear power spectrum. And that is on top of CAM.
okay.
And it's just like the standard cosmological model. We have a larger prior on NS, but NS is not really well constrained generally with cosmic shear data. So you can kind of like go wild up and down. So
No, I think that if you use a Starobinsky potential energy, you will fit very well the data.
mhm.
It's
Now I
and
haven't, yeah.
okay, yeah,
Yeah, so we're just using something very standard basically.
okay.
Yeah.
And the second question, and I finish. It's in the simulation you show on the B modes. So you use these integrals for the correlations. Have you accounted for the chirality of the B modes? Because you know that the B modes they have handedness. So do you account here?
So here it will, so the B modes in Kusebis are taking both, like both this way and the other way. So both Kelly um, uh, signal, because neither of them should occur in cosmic shear data, basically. So lensing at first order doesn't create any of these.
Okay.
So it's both of them. So the handedness is not like distinguished between them, basically.
Okay. Thank you.
Excellent. Other questions, comments? Okay, so if not, then Marika, thank you again for a very interesting presentation.